Hello learners, welcome to Dr. D.Y. Patil Vidyapith's Center for Online Learning. I am Professor Dattatray Katore and you are studying with me Statistics and Quantitative Techniques. In this video, we are going to discuss Unit 4, that is Correlation Analysis. So in this particular video, we are going to discuss scatter plot, then strong and weak correlation, positive and negative correlation, Karl Pearson's correlation coefficient, and Spearman's rank correlation coefficient. So these are the things which we are going to discuss, and this is not measure of dispersion actually. This is a correlation analysis. Simple linear correlation. So definition of correlation: if two or more quantities vary in sympathy so that movement in one tend to be accompanied by corresponding movement in the other, then they are said to be correlated. So if there is a change in one variable, other variable also changes corresponding to the change in that previous variable, then these two variables are said to be correlated. For example, demand and price. So there is a famous rule all the management students learn, that the quantity demanded is inversely proportional to the price of that particular commodity, right? So quantity demanded of commodity X is a function of price of that particular commodity, and there is an inverse relationship, negative relationship. So for example, if the price of the commodity increases, the consumption or the quantity demanded goes on decreasing or decreases, and if the price when the price decreases, the quantity demanded increases. So by changing the one variable, there is a corresponding change in the other variable, and that's why we say that these two variables are correlated. So in this case, this QD, the quantity demanded, is a dependent variable, and Px, that is price of commodity X, is the independent variable. So by changing the independent variable, or by changes in the independent variable, there are changes in the dependent variable, and these two variables are correlated. So correlation is an analysis of covariation between two or more variables. So it is an analysis of covariation, how the two variables vary with each other, with respect to each other. That is what correlation is. Types of correlation. So the following are the different types of correlation: positive and negative correlation. For example, again I will discuss the law of demand. So quantity demanded is a function of price of that particular commodity. Quantity demanded of commodity X is a function of price of that commodity, and we already discussed that if the price increases, the quantity demanded decreases, and vice versa. So what we can say, there is inverse relationship between these two variables. One variable is increasing and other variable is decreasing. So the movement of these two variables is in opposite direction. If the price of the commodity decreases, the quantity demanded of that particular commodity increases. So there is the movement of these variables in the opposite direction, and that's why the correlation between these two variables can be called as negative correlation, because the movement of direction, the direction of movement is in different direction. Now let us talk about the law of supply. So you must all be knowing what is law of supply. So quantity supplied of commodity X is a function of, again, price of that commodity. So if the price of the commodity increases, the quantity supplied by the supplier, by the seller, increases. If price increases, so he will have more incentive or more profit, and that's why he will supply more quantity to the market. And if the price of the commodity decreases, the quantity supplied in the market will also decrease, right? Because he will have less incentive. Now the profit margin will decrease, and therefore he will supply less quantity to the market. So there is a movement in the same direction. If the price moves up, quantity supplied also moves up. So movement in both of these variables is in the same direction, and that's why these two variables are called as are called as positively correlated, right? Because movement of these two variables is in the same direction. Similarly, there can be simple correlation. So simple correlation means there are only two variables, only one independent variable, and there is always one dependent variable. So such kind of correlation is called as simple correlation. Then there can be partial correlation. Partial correlation means there will be more than one independent variable, but we do not study the impact of or the correlation of all the variables taken together. For example, suppose y is correlated with or is a function of x1 and x2, right? So we study y as a function of x1 only at a time. So we study the correlation between these two variables, independent and dependent variable, taking one independent variable at a time. Then we will study the relationship of y and x2. So that is what is known as partial correlation. And then there is multiple correlation. So in multiple correlation, we study the relationship between the variable all at a time. So linear and non-linear correlation. So when there is a straight line function, we call it a linear function, and when there is a curve, we call it a curvilinear or non-linear correlation between the variables. Positive and negative correlation further explain. The correlation between the two variables is said to be positive or direct if an increase in one variable corresponding to increase in other variable, or decrease in one variable correspond to the decrease in other variable. That is, the movement of the variables is in the same direction. Then such a correlation is called as positive or direct correlation. The correlation between the two variables is said to be negative or inverse if increase in one variable correspond to decrease in other variable, or decrease in one variable correspond to increase in other variable. It means that both the variables are moving in the opposite direction. So such kind of correlation is called as negative correlation or inverse correlation. Simple correlation, it involves the study of only two variables. For example, when we study the correlation between the price and demand of the product, it is problem of simple correlation, because there is only one independent variable, that is the price, right? And there is only one dependent variable. So dependent variable is always one. So that is what simple correlation is. Partial correlation, so it involves the study of three or more variables, but considers only two variables to be influencing each other. So there may be more than one variable which may be affecting the quantity demanded, such as price of the commodity itself, price of other related commodities, then advertisement expenditure, promotion, taste and preferences of the people, and so many variables are there. So when we study the relationship between only two variables at a time, dependent and only one independent variable, keeping other variables constant, such a correlation is called as partial correlation. And multiple correlation, it involves the study of three or more variables simultaneously. So we do not keep other variables constant, and we study the correlation between the variables taken all together. Linear and non-linear correlation. The correlation between the two variables is said to be linear if the amount of change in one variable tends to be a constant ratio to the amount of change in other variable. So as already discussed, so change in one variable and change in other variable x. So if this ratio is constant, then we call it a linear relationship. In that case, we will be getting a linear line, a line like this. We have x here, y here, and the slope is same throughout the line. So you can measure the slope at between any 2 points, you will get the same slope. So change in y divided by change in x is constant, so that we get a linear diagram. Non-linear or curvilinear, the correlation between two variables is said to be non-linear or curvilinear if the amount of change in one variable does not bear a constant ratio to the amount of change in other variable. So if this ratio is not constant, is not fixed, if this is fixed, then it is linear correlationship, and if this delta y by delta x keeps on changing, it is not constant, then this is curvilinear equation. In that case, we will be getting a curve like this. So that is curvilinear correlation. So there are various methods of studying the correlation, like scatter diagram method, Karl-Pearson correlation coefficient, rank correlation coefficient. Scatter diagram method. A scatter diagram of the data helps in having a visual idea about the nature of association between the variables. If the points cluster along a straight line, the association between the two variables is linear. So what we do in scatter plot, actually a scatter diagram is also called a scatter plot. So we have x-axis, we have y-axis, and we will be having the pairs of x and y variables values. So we plot the values of y corresponding to the values of y, and we get some pattern. So this particular pattern of plots or pattern of points is called a scatter diagram, right? It can be linear, it can be curvilinear. So scatter diagram of the data helps in having visual idea about the nature of association between the two variables. If the points cluster along a straight line, the association between the two variables is linear. So if we get a cluster of points like this, so this kind of relationship is called as linear. Further, if the points cluster along a curve, suppose we get a curve like this, we get a points cluster like this, then this will be called as a curvilinear. Finally, if the points neither cluster along a straight line nor along a curve, there is an absence of any association between the variables. Covariance. So covariance between x and y is denoted by covariance of x and y. So how it is calculated? So let me tell you. Okay, covariance of x and y. So how the two variables are moving together? This is calculated by using sigma x minus x bar multiplied by y minus y bar divided by n. N is the number of observation. In case of population, we use n, and in case of sample data, we use n minus 1 degrees of freedom. So yes, scatter diagram. So we can be having various types of scatter diagram. So from this scatter diagram, okay, let me take the pointer. So if we have a diagram like this, so we can say that there is a strong correlation between the variable. From scatter diagram itself, we can judge whether the correlation is strong or weak. So if we get a scatter plot like this, we call it a weak correlation. And from this particular pattern, we are not able to identify any correlation between the variable. Now we can from this particular diagram, we can say that there is a weak negative correlation, because the movement of the plot, and when we draw a line passing through all these points, we get a line which is downward sloping. That's why this is a negative correlation. Again, this is a strong negative correlation in the last diagram. So in the first scatter plot, we have strong positive correlation, because if the value of x increases, the value of y also increases. So there is a positive correlation, and we can see the pattern is very close, and that's why it is a strong correlation. And the plot now in this particular second diagram, we can see the points are a little scattered, and from this we can know even if the correlation is positive, it is a weak positive correlation. From the third diagram, we cannot judge any pattern, right? So we can say that these two variables are not correlated. From the fourth diagram, we can say that these two variables are negatively correlated, because if the value of x increases, the value of y decreases, and when we draw a line of base fit, we get a downward sloping line. And the last diagram tells us that there is a strong negative relationship. Now let us talk about the line of best fit. So when we plot a scatter diagram or a scatter plot, what we get? The cluster of points, the pattern of points. So from that pattern of points, we can draw a line of best fit. Now what is a line of best fit? So there are two rules about drawing this line of best fit. What we can do, we can draw a line which passes through maximum number of points. This is the rule number 1. And the second rule is that you should keep equal number of points on both the sides of the line. So the line should pass through maximum number of points, and the second rule is that you should keep equal number of points on both the sides. So you can see this particular diagram. So line should pass through maximum number of points, and you should keep approximately equal number of points on both the sides of the line. So this is the way of drawing the line of best fit. And when we draw the line of best fit, we know whether the variables under study are positively correlated or negatively correlated, and whether there is a and from the scatterness of the points, we can judge whether there is a strong correlation or weak correlation. So again from this we can know this is a strong positive, this is weak positive, there is no correlation here. Here we have weak negative and here we have finally strong negative correlation. So we have an example here, making a scatter plot of a data set. Use the given data to make a scatter plot of the weight and height of each member of a basketball team. So we have height in centimeter here, height in inches here in the first column, and weight in pound in the second column. So the points on the scatter plot we have 71, 170. So 71 is the height in inches, 170 is the weight in pound. Similarly we have we have same kind of pairs, 68 and 160, 70 and 175. So these are the pairs we have for height and weight. Now for these pairs we can find out a scatter diagram. We take weight on y-axis and height on x-axis, and when we plot the weight against height, we get a scatter diagram like this. So this is how we can draw a scatter plot. It's continued. Okay, we have height in inches, weight in pound. We have some pairs, 63, 125. This is another diagram. Okay, these values are different and these values are different. So again we get a scatter diagram like this, right, when we plot height against weight. Do the data sets have positive or negative or no correlation? Yes, the data can have positive, negative or no correlation. The speed of runner and the number of races she wins. So what we can say from this? Positive correlation. The faster the runner, the more races she will win, right? So there is a positive correlation between the speed of the runner and the number of races she wins, because running fast is the running fast is the key performing area in case of running, and if the runner runs fast, then only he can win more number of races, and therefore there is a positive correlation between the speed of the runner and the number of races she or he can win. Example 2, again the size of the person and the number of fingers he has. So there is no correlation. A person generally has 10 fingers regardless of their size, and therefore there is no correlation, neither positive nor negative. The size of the car or truck and the number of miles per gallon of gasoline it can travel. So what do we say? Negative correlation. The larger the car or truck, the fewer miles per gallon or gallon of gasoline it can travel, right? Your grade point average and the number of A's you receive. So there is a positive correlation, because the more A's you receive, the higher your grade points average. So we have one more example of scatter diagram. We have hours worked and circuit board assemblies. So we have data set here, and when we plot circuit board assemblies on x-axis and when we plot hours against it, we get a scatter diagram, and when we draw a line of best fit, we get a positively sloped line. So we can say that there is a positive correlation between these two variables. Grading period and number of A's. So we have grading period 1, 2, 3, 4, and number of A's, number of A grades 5, 6, 8 and 10. And when we plot number of A's against grading period on x-axis, we get a scatter diagram, and from scatter diagram we can say that there is a positive linear correlation between these two variables. So basically there are two variables, explanatory variable and response variable, or dependent variable, independent variable. There are many ways to call the variables. So basically y is a function of x. It means that y is the independent variable, x is the independent variable and y is the dependent variable, because when we change the value of x, there will be corresponding values of y. So in this case y is response variable and x is explanatory variable. So there are many ways to call these variables. So we are basically measuring the impact of x on y. So the factor which, or the variable which cause impact, is the independent variable or explanatory variable, and the variable which is being impacted is the dependent variable or response variable. Correlation describes linear relationship between the quantitative variables. X is the quantitative explanatory variable. So x is the explanatory variable and y is the response variable. X is also called as independent variable, y is also called as dependent variable. The correlation between per capita gross product X and the life expectancy will be explored in the example. So we have per capita GDP of various countries and life expectancy of the people living in those countries. So we have data sets, right? So for Austria, Belgium, Finland, and we are interested to find out what kind of relation is there between these variables. So we plot GDP, we take GDP on x-axis and life expectancy on y-axis. So we get a scatter diagram for this, and from the scatter diagram itself we can say that there is a positive correlation, because when we draw a line of best fit from this scatter diagram, we will be getting a positively sloping line like this. Let me draw it. So how do we draw a line of best fit? We draw a line of best fit by keeping it on maximum number of points and by leaving equal number of points on both the sides. So I'm drawing it randomly for you, right? So this is how we can draw it. So we can get a positively sloped line. It means that if the GDP is increasing, life expectancy will also increase, or if life expectancy is increasing, GDP will increase. Interpreting the scatter plot. So form can relationship be described by straight line, linear, or curved line? So we can understand what kind of relationship is there, whether it is linear or collinear from the scatter diagram. If there are any outliers, deviations from the overall pattern. For example, we have a scatter plot like this, and one of the point is somewhere here, right? Now this particular point is called as outlier, because this is not, this particular point is not considered as a part of this particular cluster or pattern. So these are outliers. Direction of the relationship. So there can be positive association, negative association, or no association. Strength, extent to which points other to imaginary trend line. So we can draw imaginary trend line like a line of best fit, and we can judge how the points adhere to this particular imaginary line. And strength means what is the slope of this particular line, whether the correlation is strong or weak. So that can be understood from the scatter diagram. Then we have one more scatter plot here. Here is the scatter plot we saw earlier. So from this particular scatter plot we can say that there is a linear relationship between the variables. There is no outlier. The direction is positive, right? So this is a positive sloping line, upward sloped line from left hand side to the right hand side. So this is a positive sloping line. Strength difficult to judge by naked eye. So we cannot judge the strength of the scatter plot by eye only, and this is one of the important drawback of scatter plot. So here also we have one more scatter plot. The form is linear. Is there any outlier? No, there is no outlier. Direction positive, as we can see the line is positively sloping from left hand side to the right hand side. Strength difficult to judge by eye, so we cannot find out the strength of the relationship between the variables. Now again we have one more scatter plot. Form is linear, so as we can draw a line of best fit through all these points. Outlier, there is no outlier. Direction is negative, as we can see the line is sloping downward from left hand side to the right hand side, and that's why it is a negative. Strength difficult to judge by eye, so we cannot judge the strength by naked eye. So this is the limitation of scatter diagram. We have one more here. Form is linear, outlier is none, direction is negative, and we cannot judge the strength. It looks weak, but it is difficult to judge. Then form, now this is not a linear equation, this is a curvilinear equation. Curve, outlier is none, direction is U-shaped, and strength difficult to judge. Correlation strength, how do we judge it? It is difficult to judge correlation strength by eye alone. Here are identical data plot on differently axes. First relation seems weaker than the second, but there is no idea about it. What is the strength of the relationship? By the scatterness only we are seeing that it seems weaker. this is an artifact of the axis scaling. So we use statistical measure called as correlation coefficient to judge the strength of the objectivity, the strength objectively. So correlation coefficient is given by Karl Pearson. So R is the Karl Pearson's correlation coefficient denoted by R. Always lie between -1 and +1. So how do we interpret it? When the value of R, that is Karl Pearson's correlation coefficient, is +1, we say that there is a strong positive correlation, perfect positive correlation between the two variables. So all points on the upward sloping line. When the value of R is -1, we say that all points lie on the downward sloping line and there is a strong or perfect negative correlation between the variables. When the value of R is equal to 0, we can say that there is no correlation between the variable. The closer R is to +1, we say that it is a strong positive correlation. The closer R is to -1, we say that there is a strong negative correlation. The closer R is to 0, we say that there is a weak relationship. Interpretation of R again. So direction is positive, negative or 0. Strength, closer R is to 1, the stronger is the correlation. Alright, so we are taking positive values of R here, mode of R. So if mode of R lies between 0.0 to 0.3, we say that there is a weak correlation. When the value of R lies between 0.3 and 0.7, we are taking only positive values. We can say that there is a moderate correlation, and when the value of R is in between 1 and 0.7, we say that there is a strong correlation, and when the value of R is equal to 1, we can say that there is a perfect correlation. So from positive values of R only, the modal values of R only, we can judge whether there is a strong or weak or moderate or perfect correlation, and from the sign, whether it is negative or positive, we can judge whether the correlation is positive or negative. So these are again examples of scatter diagram. So from first diagram R is equal to 0, second diagram R is equal to -0.3. So we can say that there is a weak negative correlation. So similarly you can interpret other scatter plots also. More examples of correlation coefficient: husband's age, wife's age. So for example, there is no correlation actually. R is equal to 0.94. There is a strong positive correlation. Husband's height and wife's height, so there shouldn't be any correlation between this. So R is equal to 0.36, weak positive correlation. And distance of goal putt and percent success, R is equal to -0.94. There is a strong negative correlation. So these are the values of R based upon some experiment already conducted, and from the value of R we can predict what kind of relationship is there between the given variables. Calculating R by hand. So calculate mean and standard deviation of X. So these are the various steps involved in calculation of Karl Pearson's correlation coefficient. So we can calculate the value of R by using or calculating the value of mean and standard deviation, then turn all X values equal to into Z scores, calculate mean and standard deviation of Y, turn all Y values into Z scores, use formula on the next page. So we can use this particular formula to calculate the value of R. Okay, so let me take the pointer. Now we have alternate formula here. Why n-1 is here? Because when we are dealing with the sample data, we have to use n-1, and when we deal with population data, we can use n. So Zx is nothing but this is what Zx is: xi minus x bar divided by sx. Sx is the sample standard deviation. Zy is equal to yi minus y bar, that is the deviation between y values and y bar, divided by sy. Sy is the standard deviation of y. So you can use either this particular formula or you can use this formula. This is a direct method actually. So both of them will give you the same result. So these are the values calculating R. We have x values and corresponding y values. So these are x values, corresponding y values. So we calculate Zx. What is Zx? Zx is equal to xi minus x bar divided by sx. What is Zy? Y minus y bar divided by sy. Sy is the standard deviation of y variable. Sx is the standard deviation of x variable. X bar is the mean of x. Y bar is the mean of y. So directly we can calculate zx multiplied by zy, and from this we can calculate the value of r. The value of r is equal to 1 upon n minus 1 summation of xi minus x bar divided by sx multiplied by yi minus y bar divided by sy. By putting all these values we get r is equal to this. R is equal to 0.809. Now from this we can say that there is a strong positive correlation between these two variables. So R applies to linear relationship only. So these are the some limitations or drawbacks of calculating R. R is applicable to linear relationship only. Outliers have large influence on R, and association does not imply causation. Means we cannot find out the cause and effect relationship from R. Non-linear relationship. Now from this particular data, scatter diagram, and when we draw a straight line we get a line like this, and when we find out the value of R is equal to minus 0.06. So figure show millions per gallon. So we have speed on the x-axis and we have miles per gallon, that is mileage, on y-axis. So initially we know that if the speed is up to some fixed speed like 50 km per hour, what will happen? The average will remain minimum, keep on increasing, and when the speed increases more than 50, then the mileage will come down, right? So R is equal to 0, nearly equal to 0, 0.06, but this is misleading because there is a strong nonlinear upside down U-shaped relationship between the two variables, speed and miles per gallon. So because we know that when initially we go on increasing the speed up to some speed limit, the mileage goes on increasing, and after some speed limit the mileage decreases. So this is how the fuel efficiency is. So fuel efficiency increases with the speed up to some point of time, and after that point of speed the fuel efficiency decreases, and that's why we have inverted U-shaped diagram here, scatter plot here. And when we calculated R, it is 0.06, and this is approximately equal to 0. So this is misleading because there is a strong relationship between the speed and the mileage, right? So that's why the R is not suitable for non-linear curvilinear relationships. Outliers can have a large influence. So we have an outlier here, and it can have a large influence on the value of R. So with the outlier R is equal to 0. So when we calculate the value of R by including this outlier, we get the value of R is approximately equal to 0, and when we exclude this outlier from the data and then we calculate the R, we get R is equal to 0.8. So only one value affecting the value of R. And why it is affecting? Because it is too far away from the the cluster. Association does not imply causation. So we do not study the cause and effect relationship between the variables under study. So suppose y is a function of x, so we can judge only the degree of relationship, whether it is strong or weak, or whether it is positive or negative from the Karl Pearson's correlation coefficient. We cannot find out the cause and effect relationship. For example, we cannot find out the value of y given the value of x, and that is one of the important limitation of correlation coefficient. Additional practice example, we have calories and the sodium content of hot dogs. So what are the lowest and highest calorie counts, lowest and highest sodium levels, positive or negative association? So we can say that there is a positive association. Any outlier? Yeah, yes, there is one outlier. If we ignore outlier, is the relation still linear? Does the correlation become stronger? So I leave it up to you to decide or answer these questions. Additional practice, IQ and grades. So here we have relationship between IQ score and grade point average. So whether there is a positive or negative association, is it linear or non-linear, does correlation strong? So these are the things you can answer. You are supposed to answer or judge these things from the scatter diagram. Karl Pearson's correlation coefficient, we have a direct formula. R is equal to summation of x minus x bar multiplied by y minus y bar divided by root summation of xi minus x bar bracket square root multiplied by root y minus y bar bracket square. So where x bar and y bar are the arithmetic means of x and y respectively. So we have an example here. We have infant ID on in the first column, and then we have gestational age in weeks in the second column, and weight at the time of birth is given in the third column. So a small study is conducted involving 17 infants to investigate the association between gestational age at birth measured in weeks and birth weight measured in grams. So correlation of gestation age and birth weight. We wish to estimate the association between gestational age and infant birth weight. In this example, birth weight is the dependent variable and the gestational age is the independent variable. Thus y is equal to birth weight and x is equal to gestational age. So we get a scatter diagram like this, and when we find out the correlation coefficient by using this particular equation. So this is the equation you can use. So xi minus x bar is the arithmetic mean of x, y bar is the arithmetic mean of y. These are individual values of x, these are individual values of y, yi. Sx is the standard deviation of x, sy is the standard deviation of y. So here we calculate x bar. So how do we calculate x bar? Addition of all x values divided by the number of values. We are studying 17 infants, that's why n is equal to 17. Y bar is equal to summation of y divided by n. So this is equal to 49334 calculated from this particular data. Then again we can calculate standard deviation of x, standard deviation of y, and we can put all these values in this particular equation, and we get r is equal to 0.82, and we can say that there is a strong positive correlation between the gestational age and birth weight. So these are the formulae we can use. Now this is partial correlation. As already discussed, there can be more than one independent variable. In that case we can use either partial correlation or multiple correlation. And when we study the relationship between one dependent and one independent variable at a time, keeping other independent variables constant, we call it partial correlation. So in this case, so this R12.3 means that we are studying the correlation between 1 and 2, variable 1 and variable 2, keeping the variable 3 constant. So this is the correlation coefficient in that case. Similarly, we can calculate R13.2. So this is nothing but the correlation between variable 1 and 3, keeping the variable 2 constant. Similarly, R32.1 means correlation between 3 and 2, keeping the variable 1 constant. Here R12 is the correlation coefficient between 1 and 2, variable 1 and 2. R13 is the correlation coefficient between variable 1 and 3. R23 is the correlation coefficient between variable 2 and 3. So R123 means correlation between variables 1 and 2, keeping the variable 3 constant. Similarly, you can interpret all the formulae. Then we have multiple correlation. As already discussed, multiple correlation is the correlation between one dependent variable and more than one independent variables taken all at a time. So calculation of value of multiple correlation coefficient is done by using this formula. R3.12 means it is the correlation coefficient and we are judging the impact on variable 3 due to the variable 1 and variable 2. How do we interpret it? R3.12, it means that the variable 3 is impacted due to variable 1 and 2, right? The impact of variable 1 and 2 on the variable 3. So this is how we can calculate it. So R13 is the correlation coefficient between variable 1 and 3. R23 is the correlation coefficient between the variables 2 and 3. R12 is the correlation coefficient between 1 and 2, and so on. So you can put all these individual correlation coefficient values in this particular formula to get the value of multiple correlation between variable 3 and the variable 1, 2. So here in this particular case, variable 1 and 2 are the independent variables and variable 3 is the dependent variable. So then we have Spearman's correlation coefficient. The correlation coefficient measures the rank correlation, and this technique is applicable to determine the degree of correlation between the two variables in case of ordinal data. So when we have ordinal data, the data which is arranged according to some priority, some rule, then we get the Spearman's correlation coefficient. So we can assign rank to different values of a variable with ordinal data type. So when we assign ranks, it becomes ordinal. So we have height here, VS, S, L, T and VT. This is categorical data, and we have t-shirt sizes XS, S, L, XL, double XL. Right, these are the values. Now we can assign some ranks to it. For XS, extra small, we assign 11. For small, we assign 12. Large, 13. Extra large, 14. Extra large, 15. Similarly for height, very small, small, large, tall. Sorry, it is short, very short, short, then L, then tall and very tall. So we can again assign values to it, and we can judge the Spearman's correlation coefficient from these values. So Charles Spearman's correlation coefficient, the rank correlation coefficient can be defined as RS is equal to 1 minus 6 multiplied by summation of di square divided by n in bracket n square minus 1, where di is equal to difference between ranks of ith pair of two variables, n is equal to number of pairs of observations. So by using this particular formula, we can calculate Charles Spearman's correlation coefficient. So this is the data we have, the hypothesis that the depth of the river does not progressively increase with the width of the river. So this is the hypothesis we want to judge. A sample size of 10 is collected to test the hypothesis using Spearman's correlation coefficient. So we have sample, we have data of width in meter, depth in meter, and we have to judge that whether the depth of the river increases or decreases with the width of the river. So we assign some rank, right, 5, like 5, 4, 3, 2, 1 to the data, and here is the example. Here is the solution. Sample, 10 samples are there. This is the width. Now width is increasing, so starting from the largest observation, which is 500, we assign it rank the 1. Then the next largest is 450, we assign it rank of 2. Then the next largest is 400, we assign it rank 3, and so on. Similarly, we assign the rank to depth also according to the numbers. So the largest number is 104, and that's why it is assigned the rank of 1. Then we calculate deviation. Deviation is the difference between the rank. So 10 minus 10, let me take the pointer. 10 minus 10 is 0, 9 minus 9 is 0, then 8 minus 8 is 0, and so on. This is how we calculate the values of D. Then we calculate the values of D square, squares of deviation. 0 square is 0, 0 square is 0, minus 1 square is 1, 1 square is 1, and so on. So summation of D square, summation of all these values is equal to 4, and when we put all these values in this particular equation, we get the Spearman's correlation coefficient, which is 0.9757, and it shows that there is a strong positive correlation between the variables. So thank you so much for watching this video. We studied correlation coefficient, both Spearman's correlation coefficient and Karl Pearson's correlation coefficient. Thank you all.